So in ice tables part 1, I gave you all the concentrations, and you just had to calculate the KEQ expression, which is products over reactants. In this part, you'll get the KEQ, but you don't get all the concentrations. Okay? So we get a slightly different ice table. Because we don't know the concentrations, we're going to have unknowns in the ice table. All right? I just use X. You can use whatever you want. Okay? So we have to write a let statement, or you have to define what your variable is going to be. In this case, I'm going to use X. So we're going to be looking at this reaction right here. Hydrogen gas plus iodine gas goes to hydrogen iodide. It has a KEQ of 55.6 at 700 degrees. If we look at this, the initial concentration of H2 and I2 is 0.2 molar. Okay? So we have the initial concentration, 0.2, 0.2. We have no HI. That's all we get. We know the KEQ as well. But we don't know how much you have at equilibrium. Okay? So we have to say, well, we're going to lose. We know the reaction is going to go to the right. Correct? Because we've only got H2 and I2. The only thing this reaction can do is shift to the right. So we're going to lose some H2. We don't know what it is. Minus X. Now, as soon as you're using an unknown, you have to define what that unknown is. So up here, I'm just going to say, I mean, you would do it down here, but I'll just, there's space up here. We're going to say let X equal change in concentration of H2. It could have been I2. It doesn't matter. You get a choice here. Okay, that's why we have to define it. So if I lose X amount of H2, how much I2 am I losing? X. It's the same. It's a one-to-one relationship, right? So minus X. How much HI am I gaining? Plus 2X. So at equilibrium, H2 is going to be 0.2 minus X. I2 is going to be 0.2 minus X. And HI is going to be 2X. Okay? Then we write the equilibrium expression. Or the KEQ. So KEQ. What's the KEQ expression for this reaction? There you go. Concentration of HI squared over the concentration I2 and H2. We know what KEQ is. It's 55.6. So mathematically that becomes 55.6 is equal to HI is 2X. I2 is 0.2 minus X. And H2 is 0.2 minus X. So now we got to solve for X. Log it. You could if you really wanted to, but that's going to make it way more complicated. All right, what do you notice about the bottom, the denominator? They're the same, right? So that's 0.2 minus X all squared. The top, I'll just write, you know what, I'm going to leave it as 2X squared. Okay. What can we do to solve this? Yeah. Don't expand it. All right. Don't expand it and create a quadratic, people. You can if you really want to, but don't do that. All right. If you square root both sides, all right, square root of 55.6 is 7.457. Go up here. If you square root the right-hand side, what do you get? 2x over 0.2 minus x. And now it's just a grade 10 algebra problem? 9? Grade 9 algebra problem. So multiply this up. Algebra it. And you should get... Please make sure you can do that. I'm going to let you do that because I actually want you to do this. Did we get it? Okay, so that's x. But what is the question asking for? Determine the concentration of HI when equilibrium is reached. So I want to know how much of this I have, right? What does X represent? The change in H2, right? Or I2 or whatever, it's the same thing in this case. So if we lose so much X, I could calculate how much H2 I have. If I want to know how much HI I have, it's 2 times whatever X is. Okay, so concentration of HI is 2 times 0.15. What units is this in? It's not quite moles. It's going to be molarity. You can use molarity in your ICE table because everything is contained in the same volume. All right. So if these are all in molarity, then this can be in molarity. Okay. Because I didn't give you the volume of the container. So 2 times 0.158 molar gives me 0.315. Is the concentration of HI. I probably rounded incorrectly. If you put 0.316, I'm fine. I'm willing to bet I rounded incorrectly. And since it has an 8 on the end, I'm going to bet that it's a 6. So that makes way more sense. 6. There you go. Okay. We okay with that? You're just putting an X into the ICE table. Everything else is basically the same. The KQ expression is essentially the same. All right. Next example. Carbon monoxide, water goes to carbon dioxide, hydrogen gas. KQ is 10 at 690 degrees. The initial concentration of H2 and CO2 is 0.4. Determine the concentration of CO when equilibrium is reached. Okay. So we have 0.4 molar H2 and CO2. 0.4 molar, 0.4 molar. Okay. Which way is this equilibrium going to go? It's going to go to the left, right? Or correct? How's that? That's a better way to say that. It has to because you only have products. You only have CO2 and H2. If that's the only thing in the container, it has to go left. So you're going to lose a certain amount of those. As soon as I say put an X in there, I have to define what X is. So what is X going to be? Do you want it to be CO2 or H2? That doesn't actually matter. Has less what? So we're, I should say the change in. Can we, actually, I'm just going to write it this way. If I say delta concentration of H2, is that okay? Does everybody understand what that means? All right. The change in the concentration of H2. All right. So at equilibrium, we have 0.4 minus X, 0.4 minus X. Nope, nope. These are all 1 to 1, so that's easy. And then it's exactly the same, peoples. KQ. KQ is 10. Is that what people got? 0.096 or something close. Ooh. So if that's what X is, what am I asking for? Concentration of CO is going to be equal to that. Are we okay? Yeah? All right. You don't have to do 1 and 2 unless you really want to. But you should do 3 through 8. Number 9 has a trick. I can talk about that later. I'll give you a bit of time, and then we might actually start the next one. That'll give us, no, then that'll give you more time to review in class, which is a better thing.